Ready or not, here I come. You can't hide. Gonna find you and take it slow.
Today I'll be going over sequences. So, just a brief overview. A sequence. So, often I'll be abbreviating this with SEQ. So, just for your future reference. So an example of a sequence is, this is a pretty common one. 1, 1/2, 1/4, 1/8. Okay, and so on, ... And the what is called the general term for this, so it's kind of like a general formula for each term, is 1 over 2 to the n power, where n is greater than or equal to 0. So first of all, as you can see here, n equals 0, right? Because if you have 1 over 2 to the 0, that would just be 1 over 1. So that's how we get our 1 here. This is the term when n equals 1, because then you have 1 over 2. This is the term when n equals 2, n equals 3, and so on, right? Okay, so there's another special kind of sequence called a recursive sequence. So recursive sequence. So this is when so when the term that you're looking at is when this depends on n minus 1. So this, even though it might look a little bit fancy, this term here basically just means the term that comes right before the one you're looking at. So for example, let's say, here's an example. We have the general term, an equals 2 over n minus 1, okay? And for these kinds of sequences, you'll be given an a1 to begin with, okay? So given a1 equals, let's just say, make it simple and make a1 equal to 1. So to find a2, then, you would get 2 over and then you plug in the 2 for the n spot, minus 1. So then you actually just get 2 over a1, right? So to find your second term of this sequence, you'd have to have the first term. All right, so 2 over, and we plug in what we were given, which is just 1. So then we get 2 for our second term. And then, just to expand on this, the third term, a3, would be 2 over, and then you plug in a 3 for n, so a3 minus 1 equals 2 over the a2, which is the second term we just found, right? So now we're going to plug that one in, and for a3 we get 2 over 2, which is just, and we're back to 1, right? Okay, so next slide, we'll visit the following topic. So now we're going to be concerned with the limit of a sequence, okay? Because we just love limits in this class, so we're gonna find ourselves the limit of a sequence. So there are a couple things. This is kind of the formal definition in your book. So basically, if there's a number m, capital M, such that okay, so now I'm going to get a little bit technical here, but then I'll explain what all of this means. So absolute value of an, so the nth term, minus L, is less than this e, backwards e thing, for all n greater than this big M. This is the same big M, right? Then we have limit as n goes to infinity of an, this is our sequence, equals L. Or we could also write, this limit thing is also written as an goes to L, or it tends toward L. So yeah, so if this happens, then it is said that an, the sequence, so we denote sequence by these fancy brackets. So this means sequence of an. So then we say this converges, that sounds familiar, right? Converges to a limit L. Okay, so basically, well, I'll also write the other two options. So if the limit doesn't exist, if limit does not exist, and I'm just going to abbreviate here, then we say that an diverges, the sequence diverges, right? And furthermore, kind of a more specific case, if terms increase, I'm just going to abbreviate again, increase without bound, so they just go up to infinity basically, we say that an, sequence an, it also diverges to infinity. That's just a more, to infinity, a more specific case. Okay, so this thing right here, what we're saying is the difference between our nth term and the limit value, or yeah, whatever this limit value is, it has to be less than a very insignificant number. So this is a really tiny number. So tiny number. Okay, so we're just saying that this is kind of like the normal limit definition for functions as well. We're just replacing the f of x with an instead, the sequence. Alright, so let's see, what do we have here? Let's do a quick example of what you could see about the limit of a sequence. So, example, let's say we're given the following sequence. An equals n plus 2 over n. And then we have to prove that limit of this sequence as n goes to infinity, so limit of this sequence, which is an, equals 1. Okay? So, we'll start with the definition that I was saying before, is that the absolute value of our sequence minus the limit, whatever our limit is, has to be less than a really tiny, insignificant number. Okay? And this is for all n greater than some big M. Okay? This part will come in on the second portion of this problem, so I'll show you how to use that as well. So the L that they give us is 1. So this is like our big L, all right? And we know an, so we could plug this in for that spot. So L is 1, and that is that. So we could say n plus 2 over n minus 1 is less than or equal to this like backwards e thing. Okay? So then this part here, that's actually, let's get a common denominator. So then we get n plus 2 minus n all over n, right? Because this was the minus 1 here. And then less than e. And you see how the n and the minus n on top cancel, so that's good. And we get 2 over n is less than e. Okay? So then we know that this, okay, so what we started with here, this is part of the definition of the limit. This is basically another way to write that, okay, because we just subbed in the given sequence and the given capital L, okay. So this is going to be true. This second, well, the first statement and the second statement are both going to be true when, and we can, I'll just rewrite it over here. So now we're going to find our big M for which n has to be bigger than for this statement to hold true. So here you just solve for n basically. So we're going to multiply by n on both sides. So then this is the fancy e with times the n, and then divide by the fancy e. And we get that n, I'm just going to flip it around here. So n has to be greater than 2 over this e thing. Okay? And see how this is in the form of this now. So we know that m, which is on the right side, has to equal 2 over e. So m equals 2 over fancy e thing. Okay? And then as you'll see, there's another example in the book as well. It has a similar formula, but basically once you get to this step here and you find a definite capital M, then this is proved. So convergence, or the limit, is proved. So that's good. Alright, now on to another theorem.
Ready or not.